Okay. Okay. So let me start then. Okay. Can you hear me properly? Andres or Sage, can you confirm?
Yeah,
Okay.
everything is
Thank you. Fine.
fine.
Okay. Fine.
Yes. Maybe before you just start this one, I want to ask a question concerning the assignment that is you created. I didn't know if you have talked about it.
What did you say?
There's an assignment you created.
Assignment.
Yes.
Okay, I have just uploaded it. Next semester, from next semester, sorry. From the next week, I will discuss about it. Next week.
Okay. Okay.
Next week.
Okay.
Yeah.
All right. Thank you.
Because this semester I plan to cover up some introduction sections, and then next week I start with the exercise. It would be next Tuesday, most probably. Right? Okay. So in the yesterday class, we discussed about the definition for the stability, and we discussed some of the common terms which we use for stability analysis. And from this slide, we have the we start with the how we classify the power system stability. And as you can see, this classification, the first one is on the basis of what is the system variable associated to stability. So depending upon the state variable, I mean, or the system parameter, we can say rotor angle stability, frequency stability, and voltage stability. Because voltage, frequency, and rotor angle, these are the quantities, system quantities. So based on the quantities, we have three different types of stability. Next one, we refer to amount of disturbance. And in respect to the amount of disturbance, for the case of rotor angle stability, we have a small signal stability, and we have transient stability. Now, in respect to the small amount of disturbance, stability associated with a small amount of disturbance, so it will be as a small signal stability. And for this case, we are concerned about the stability analysis for time duration in the range of 10 to 20 seconds, a comparatively larger duration for a linearized system. We call it small signal analysis we perform for a linear model. But transient stability, it will be for a larger disturbance. And in this case, the time duration for analysis, it is just 3 to 5 seconds only. So since because of large transient disturbance, the behavior, the dynamic variation of rotor angle stability could be much more. And thus, it is more important to analyze the system stability for a smaller time duration. Now, both small signal and the transient stability in respect to the rotor angle stability, they fall under the short-term stability here, stability analysis. In respect to the frequency stability, we have it as a short-term stability and a long-term. And for the case of short-term, when we have the frequency stability analysis, it will be for time duration 10 to 30 seconds. But for a long-term frequency stability analysis, it is comparatively much larger, much longer duration. Yeah. Then the next one refers to the voltage stability. Here again, it is categorized as a large disturbance voltage stability and a small disturbance voltage stability. But again, both forms of voltage stability, small and large, they can be either as a short term or long term. here, and it can be in the range of a few seconds to even tens of minutes. So for long term, it will be, that means several minutes, but for short term, it could be just few seconds only. Because when you look at this, if you refer to this slide here, which I had yesterday, and when you look at, when you observe it, you find here that rotor angle stability. This is the in its deviation in the rotor angle with respect to this bus here. What you find here that from 2 seconds onwards, and you can see that by 6 seconds, that means within 2 seconds, 4 seconds here, right, or 6 seconds here, something, the deviation is much larger here with respect to the gamma was here. So that means instability in the rotor angle is observed just in few seconds, 3 seconds, 4 seconds, 5 seconds here. Similarly, when you look at the voltage angle instability, as in this case, so you observe that uh, from here onwards, the let's say 10-21 second onwards and up to 30 seconds. So that means within 8 to 9 seconds here, the bus voltage drops progressively. So that means in this much time duration, the bus drops progressively. So again, it is in the range of 8 or 9 seconds, something here. Uh, and thus, but in some cases, the voltage drop, the progressive drop in the voltage could be in a longer time duration, and that could be in the range of minutes here. And thus, we have long-term voltage stability analysis here, right? To give you more info about the different forms of stability, I have this slide. And here we talk about the rotor angle stability. So in fact, from the earlier definition which we had for pulses stability, so if you define it for rotor angle stability, we'll say it is the ability of the synchronous machine in the interconnected system to remain in synchronism after being subjected to disturbance. So this is the rotor angle stability. So that means ability of the machine in the interconnected system to remain in synchronism after being subjected to disturbance here. Now, if there is a occurrence of instability, rotor angle instability, we will observe an increase in the angular suppression. That means the angle, the rotor angle suppression between the generators, uh, resulting into the loss of synchronism with respect to the other. That is to say, if we look at this figure, here we have the rotor angle difference here, right? So you can say earlier it was very small rotor angle difference between the generators. And here it is shown, you can see here. Remember one thing, when you talk about rotor angle stability, we have said that it is the relative motion of one generator with respect to the other, right? Or it could be the relative motion of one generator with respect to the complete network. So what we have shown here, it is the rotor angle difference between the generator 10 and generator 1. So here we are analyzing the dynamics of generator 1 with respect to all the generators in the system. So we have taken the relative angle difference actually here, relative motion, that means the difference of the rotor angle between the two generators. And we are analyzing it for generator 1 with respect to all other generators in the system. So we have the rotor angle difference. We have the rotor angle difference along this axis. So what you observe that some of the generators here, that means the angle difference for these generators here, they are of this variation. Some other sets of the generator here, mostly those with the black colors here, they are of this much dynamics here. And then you find that one of the generator here, it is the generator 9, the rotor angle difference between 9 and 1, generator 1. What you find is that it is deviating out here. You have a up to, in fact, you find that, let's say that at this instant of time, there was some disturbance here at this instant of time. And following the disturbance, the generator rotor angle deviation in some group of the generators, they follow this trend. For other sets of the generator, they follow this trend. But for one of the generator here, generator 9 here, and the generator 1 with respect to generator 1, what you find here that rotor angle reaches to the peak here. It reaches to the peak at 0.5 second, and after reaching to this peak at 0.5 second, it does not come back. It does not come back here. It does not decrease further, yeah, after reaching the peak. Instead, it deviates out from the first peak occurrence here. So this is what we say that the generator 9 is forming a instability here. So that means, and moreover, we observe that the rotor angle of generator 9 it deviates out on the first swing. So this is the first swing here, right? The first swing here. And this we call it as first swing instability occurrence for generator 9 here. However, for other generators, when you look at these groups of the generators, in this case, the rotor angle reaches to the peak and then it goes back. And then again, there are some more swings. In fact, you can say this is one cycle. In fact, this is one, you can say, half cycle, and this is another half cycle. So this is one complete cycle of swing of the generator angle here. So this is one complete cycle here. So in that sense, uh, for other generator, you observe that they have comparatively much more deviation in the swing. The amplitude of deviation, the amplitude of oscillation for these sets of the generator, they are comparatively much more with respect to these groups of the generator, right? And now this stability depends upon uh, your ability to maintain or restore the equilibrium here between the forces, between the electromagnetic and the mechanical torque of the machine here in the system, right? Do you have some comment on this deviation, particularly the one which you observe here? Anybody can comment what you observe?
They seem larger than the green
Yeah,
ones.
that's true. But I'm saying particularly for those generators which are shown in the black color here. Now, if I
They are
say for
going back to zero now after,
okay,
because the deviation is in decreasing.
okay, but if you look at these, these groups of the generator, they are swinging in the same phase. All right. Just see
Mhm.
all these generators, they reach to the peak, positive peak simultaneously. All the generators reach to the negative, you can say, peak simultaneously. So that means these groups of the generators, they are coherent to each other, at least for few swing, at least for few seconds, few swings here, right? But if you look at these groups of the generator, particularly if you look at this curve, this curve, right? What you observe that this group, this generator, particularly in this time period, the behavior of this generator, it is actually, here you find it is positive peak, but other group of the generators, they are with a negative peak here. Similarly, here they are with a positive peak, but this group of the generator, it is negative peak. So for this time period, this group of the generator, it is in opposite phase. It is in opposite phase with respect to other group of the generators here. So it is possible that following the disturbance, some group of the generators, they will swing in the same direction. for certain duration. And again, it's not necessary that they will swing all together for the entire duration until they settle down finally. Not necessary, right? And while some group of the generators, they may swing in the same direction for certain duration, and for remaining the duration, they may swing in the opposite direction. That is also possible. And in some case, it is also possible that they may swing in a at a different phase angle shift actually, because when you look at this, generator has the peak at this time duration, while this is lagging behind. So this generator reaches its peak at this time period. That means the first swing peak, the peak of the first swing of this generator, it is lagging behind this one. Yeah, so that is always possible when you have several generators in the system, and following the disturbance, the dynamics of some group of the generators, they could be the similar for remaining group of the generators, they could be similar for certain duration, and then following time period, their behavior could be a little bit different. Thus it is very important to analyze the system generator behavior dynamics following any disturbances here, right? Okay, anything on this? So we
Yes,
okay.
I have
So
a question about this.
yes.
What difference does it make when you have a generator swinging in the opposite direction? Is it more severe, or is it going to be lead to more instability? Or is there anything in particular that we have to know about this? Or
Yes, because if the if the two generators, they are swinging in anti-phase, in opposite phase, that becomes much more problematic actually. If they are swinging in the same direction, then it is different. Then actually, just remember one thing. Uh, it is very important to damp out these oscillations, all right, because there should not be the generator angle oscillations here, all right. So because otherwise this oscillation of the angle will translate, I will show in the next slide, it will translate into the oscillation of the power flow in the line, and thus you cannot have increased loading on the line. That means you cannot have more power flow. Uh, let's say that you have two generators interconnected by a line, and you have a power flow of some 500 megawatt. But if there is a need for more power flow in the line, although the maximum loading can be up to the surge loading, or it could be even up to thermal loading capability of the line, but normally we have loading comparatively lower. So but if there is oscillations of the generator, um, particularly if it is in anti-phase, right, opposite phase, then we cannot have more power flow in the line, because there it is there are chances that the one generator, as you can see here, as you can see here, this generator, it is deviating out, it is deviating out with respect to one here, right? So generator 9 goes, it is deviating out, so that means the angle difference of generator 9 with respect to the one, it is going out, and thus that means the generator 9 is losing the synchronism here, it is losing the synchronism, and thus the generator 9 becomes unstable here. So thus it is very important that in fact antiphase is much more problematic as comparable to the similar phase of oscillation, I can say, right? So if maybe I have with this slide I want to show what is the oscillation here. Now from this relationship, when you look at, this is what we say, the power flow. So what is shown here, this is the bus. Yeah, we have two generators connected to the ends of the bus here, and we have the load here, right? We have the bus voltage at the two ends, And let's say this we have shown it for silent shape generator to be more clear about the angles. It could be also cylindrical shape, doesn't matter. What you find here that the initial angle of generator 1, it is 35 degree here, and the initial angle of generator 2, it is 72 degree here. And the equation for the power flow between the two buses here, right? It is this one. This is the power equation for the power flow, and it is the written as the product of the voltage magnitude at the two end, and it is a sine function, that is delta. And this is the rotor angle. It is actually the difference of the two angles here at the two ends. And this is the, you can say, the reactance of the line here. Now with this case, if there is some disturbance, let's say, right, what you find here that the generator angle here at the two ends, right, it will have some oscillation. It will have some oscillation here. And as you can see, this generator 1, it is going positive. However, generator 2 is going negative here. So it means that the two generators will be oscillating in anti-phase with respect to each other, because the first swing which we observe, the first half cycle which we observe, all right, and then the complete cycle, it is anti-phase here, right? So thus the two generators, they are swinging in opposite phase with respect to each other. And as a result, what you find here that the angle of oscillation, let's say, it is same. So the angle of oscillation, it is about 5 degree here. And for one cycle, if you calculate, so one cycle completes in 10 seconds here. So what will be the frequency of oscillation here? What is
0.1 hertz.
1 by 10 hertz?
Yeah, 0.1.
So 1 by 10 hertz, that is the frequency of oscillation for the generators here. And because of this oscillation, it is very low hertz, because your system frequency is 50 hertz. Your as a voltage signal, it is 50 hertz, current signal is 50 hertz here. But generator angle oscillation, which we call it, this is the rotor angle oscillation, it is very small hertz. And again, it takes place between the generators which are connected by a tie line here. Two generators at far away and we observe the rotor angle oscillation between the generators here, right? Very low hertz here. But because of this rotor angle oscillation, and since it is this angle which is oscillating, and thereby the power flow, and thereby the power flow which between the buses, that will also oscillate. And this oscillation, because you have an oscillation of something 5 degree here, so thus the amount of the power flow from bus 2 to bus 1, because steady state value, it is 100 megawatt. The steady state power flow is 100 megawatt, but because of the disturbance and following the oscillation, this steady state power flow, it is associated with plus minus of 10 megawatt. So that means you have a power flow oscillation with a magnitude of 10 megawatt here. So thus the power flow through the line will also oscillate in this range, in this magnitude. And thus sometimes we say rotor angle oscillations, or we say the power oscillation, the power oscillations here. Okay. So we call it as low frequency power oscillation, this one, because it is a very low hertz. So sometimes we say it is a low frequency power oscillation. Okay. Right. Any question on this?
Yes.
Yeah.
With respect to the direction of the power flow,
Yeah.
well, we will consider the angle difference between them. From what we have, Q2 data 2 is higher than data 1. Is that the reason why there's a power flow from V2 to V1?
Uh, yes, because the initial angle, the steady state angle of bus 2, it is 72 degree, and however for 1 it is 35 degrees, it is more, and thus the power flow is uh, from bus 2 to bus 1 here. Yeah,
All right,
because
thank
it
you.
is at much more angle. Because remember one thing, uh, let's say this is the generator which is connected to this bus, and this is the generator another connected to this bus. Now what will be the bus voltage? Will it be same or different?
It will be different
Different means what? What do you mean by different?
because there is some power flow between them, so there must be some voltage
There will
difference.
be some voltage drop.
Yes.
Okay, but it cannot be like saying that this is a 132 kV bus and this is 400 kV bus. Can it be this way?
No, 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 no.
No,
No,
it
not
will be
that
the same.
much.
It will be the same bus voltage. If it is
Yeah, but
400 or
slightly
it can
different.
be 400, but there will be some
Yeah,
voltage drop, that I agree. But that
yeah.
means the difference in the voltage magnitude between V1 and V2 will be almost similar. It will be the similar voltage magnitude. Okay, so that's the power flow in the line. The power flow in the line, because this is constant. Let's say this is constant. The bus voltage is also constant. Let's say almost V1 and V2, they are almost constant, right? If I say this bus voltage is something, because the power flow is from bus 2 to bus 1. So let's say this is, I will consider this as a reference value. So this is 1 per unit here. Okay, I'll say this is 1 per unit. And since this is the direction of the power flow, so what will be the voltage here with respect to this 1 per unit? It would be
Maybe
something
0.95.
0.98, 0.99, right? So that will be the difference in the voltage here between the two. And thus the amount of the power flow, thus the amount of the power flow for a given voltage and the reactance of the line, it is altogether dependent upon what is the angle difference between the two generators here. So if you want to have more power flow, then obviously the angle has to change, angle has to be more. Yeah, that we do it by governor setting. Yeah, we will have more amount of power flow, and thus, but again, uh, what could be the angle difference? What could be the maximum angle difference? Yeah,
90 degrees.
okay, 90 degree is okay. That could be another, but let's say if it is 180 degree.
Yeah, yeah. The absolute maximum is 180, but I mean 90 is the maximum power you can get.
Yeah, that's fine. But if it is 180 degree, then what you say?
It's like they're opposing each other. I don't know.
Then it is system is unstable. Then the system will
Uh-huh.
become unstable. Because
Okay.
when you look at this curve, if I have to draw here, because this represents the sine function here. So because here you have the P and this is your angle delta. So this is the sine function here. Am I right? From sine delta, if you look
Yes.
at, yeah.
Yes.
This is somewhere you get the maximum power transfer. When the angle difference, it is 90 degree. But even at this point, you can have some power flow if the angle is here, right? But if the angle difference is 180 degree, then the power would become 0. So it is very important that the angle difference between the generators should not reach 180 degree, because if it reaches 180 degree, the power is reduced to power flow reduced to 0, and thus the generator will lose synchronism. This is very important, and thus it is very much right that the angle difference between the generators should not be 180 degree. It should not be 180 degree. Otherwise, the generator will lose the synchronism. Yeah.
Okay, so what about the situation, or I don't know if you have had or heard about the situation where the two generators, they are having the same angle and oscillating in opposite direction. Have such happened before?
You mean it is the same magnitude of oscillation, but in opposite direction.
Yes.
Yeah, it can happen. Yes, it can happen. Yeah, yeah. If you look at this one, if you take this example here, I said that uh, the angle of oscillation, the amplitude of oscillation between the two generators to be 5 degrees. I said, right?
No,
So
I'm not talking of the angle, the oscillation angle between them. I'm talking of the theta 2 and theta 1, if they are the same but rotating in the opposite direction.
yeah, this is opposite direction only, because when you look at this one, this is going positive, but this is going negative here. So
I
that's mean
think
that
he means that the value itself is the same, like 72 and 72. They start from the same value.
Yes.
you made so the initial value.
Yes, initial value is the same.
Okay. But if you take initial value for the two generator to be the same, how can there will be a power flow?
It will be oscillating around zero.
Yes,
right?
that's what I'm asking. If you have had such situation in
No.
recent.
Just remember one thing. If you want to have some amount of the power flow at steady state condition, there should be some angle difference. Yeah. So if you want some amount of the power flow through this line from bus 2 to the bus 1, okay, this is 72-degree. Here it could be 70-degree. Here it could be 70-degree. But the amount of the power flow will depend upon what is the angle difference here. It is only 2 degrees. So thus the amount of the power flow, steady state power flow will be very small here. The steady state power flow will be very small. So if you want to have more power flow, then in that case, the angle difference has to be more. And if you say 72-degree here and 72-degree here, then there will not be any power flow. There has to be some angle difference between the angles, I mean, the bus angles or the rotor angle. If you want the power flow, there has to be.
Okay. So
There has to be.
this would have led to a critical disturbance.
Critical disturbance means?
What I mean that it will be a serious fault that needs attention.
But one thing I can say, let's say I have shown it for one generator. This is a large generator, right? Let's say you have some more generator here. You have some more generators, right? You have some more generator. That is okay. Now, in that case, since you have several generators here, they are connected to this bus, and you want the power flow here in this direction, then you can regulate the generator angle of all the generators here to be the same value. You can regulate such that you have the power flow in this direction, and the generator angles of all these generators which are connected to the common bus, they are same. That is possible. But the angles of these sets of the generators and the angles of this has to be different if you want the power flow here. They have to be different, right?
All right, thank you.
Because there cannot be power flow if the angle difference is 0. All right. So if you want the power flow to the line, then there has to be angle difference between the two ends here. There has to be. That is has to be. It cannot be the saying that the bus angle or the rotor angle of the two generators at both ends to be the same. Then there will not be any power flow. Not a power flow. Right. So here we have it is just a brief description about what is voltage stability. Again, it refers to the stability, that means this ability. Yeah. It is the ability of the power system to maintain steady voltage. That means the buses in the power network should be able to maintain the voltage constant. So that means there should be a steady voltage at all the buses in the network. Yeah. Following the disturbance from the initial operating condition. So it refers to the ability of the power system to maintain a steady voltage at all the buses. There should not be a drop in the voltage or the rise in the voltage even at one of the bus. It says steady voltage means You can say constant voltage. Okay, there should not be any deviation. There should not be any deviation at all the buses in the network. So that means you don't allow any deviation at any of the bus here. All right, any of the bus in the system. Otherwise, that bus will lose the stability. All right. So it is very important that we are able to maintain a constant voltage at all the buses in the system following the disturbance here. So this is just a graphical shown, and what we find here that along this axis we have the voltage here, right? Uh, Now you can say that if in the system, when you don't have any power flow, so there will be a rise in the voltage. Do you think it is okay to say? It is not shown 100% here, but it is shown something 105%. Is it
Yeah,
okay to
that
say?
makes sense. Yeah.
Why?
1.05 per unit, right?
Why? But why you say this?
Because there is no power flow, so the
Okay,
voltage
so
will
then
rise. It will be no load condition.
then the no load voltage should be the per unit. It should be 1 per unit.
No,
But why
the no
but
load is usually higher than 1 per unit. The 1 per unit is the rated voltage, right? Not the no load voltage.
but why it is higher? That is the question.
I don't know. Okay.
Okay. Just see. Normally, voltage stability. We discuss for high bus voltage. Actually, it could be 230 kV, it could be 400 kV, it could be 765 kV, and so on. Voltage stability, we generally we don't discuss for 400 volt, or maybe for a distribution network we don't say it for, or maybe for 11 kV line or 33 kV line we don't say it for that. Voltage stability, mainly we say it for much higher voltage. But okay, you can argue that nowadays,
Why is that the case? I
sorry,
mean, the distribution voltage is also very important, right? To
important.
keep.
Yeah, that's what. Yeah, that's why I was coming to your point. But nowadays, since we have the renewable resources being connected at distribution level, so in that case, we now talk about the voltage profile being maintained even at distribution network. We talk about yes, yeah. But coming to this, why we have this 105? Because earlier we talked about the voltage stability for a transmission network, much higher voltage, and for a transmission network, mainly for EHV, more than 220 kV lines or 365 kV line, 400 kV lines, the capacitance of the line, overhead line, I mean, right? Okay, the capacitance is much more prominent than inductance of the line. And because of the capacitance being higher, the inductance of the line, there is a charging current flow, right? Capacitive current flow. And thus it results to a higher voltage at the bus end here. And thus that's why it is said that, okay, at no load, the bus voltage, it is slightly higher. And that's why it is setting, let's say start from 105%. It can be even from 100%, 1 per unit as well, no doubt about it, right? Now, as we increase the load here, as we increase the amount of the power flow through the line here, what you find that the voltage at the other end of the line drops, because there will be some voltage drop, right there, because the line is merely inductive in nature, and thus and again your load is also inductive in nature, so there is a inductive current flow. It's not capacitive current flow. So because of that, you have a voltage drop to the line. And then it, depending upon if you have a much high power amount of power flow through the line, then a point is reached wherein if you increase the power beyond this, the voltage will suddenly drop to zero, and that we call it as knee point of the PV curve here. So this is the knee point where you find that the voltage collapse. There is a voltage collapse at the bus for the amount of the power flow beyond these points, and thus this power flow we call it as critical amount of power transfer here. Although it is set about 70%, but in some cases it can be even 80% as well. Yeah, it could be. But normally for the bus network operation, for the amount of the power flow, we say that at least for the transmission network, the voltage variation, the voltage deviation of the bus network should be just 5% around the nominal value, around the rated value. It should not be beyond that, right? So here, so what? So as said, because of the voltage instability, and thus that is the collapse of the voltage. Normally, this voltage instability is because of increased amount of load connected to the bus here. So if you have a high amount of the power drawn because of the load connected at a given bus, the voltage will drop. So mainly voltage instability is because of high amount and highly inductive load being connected at the bus. Yeah. So this could be because of the voltage instability occurrence. Uh, you may have loss of load. You may have the loss of integrity of the power system. That is possible. And here it shows what could be the time duration, time frame for the voltage stability. It could be in the range of 0 second, 1 second to up to 30 seconds here. We have this because let's say you have a high amount of or a large motor connected to the bus here. So because of a large induction motor being connected to the bus, it will draw a high current here, and that could be this one. And then another one is the oils. That is actually in fact I am not able to recall this exactly. What is oil? This refers to the optimal setting of the electronic loads here, I think, but I'm not sure about it. I can say about this one. Then this is for the short term stability, voltage instability. Then for the long term, this duration could be up to 60 minutes. So that means 1 hour or something. Yeah. And here we have the use of type changing transformers or the voltage regulators in action here. So that could be another way. And again, oils, that is basically, I think it refers to the compensators here, I think, reactive power compensators here. Now this slide, now we have voltage instability or the rotor angle instability, and but how they are related to each other. Are they independent of these two forms of instability? Are they independent of each other, or there is some form of interdependency? What do you say about it? Yeah, tell me.
I think they are related.
They are, because just see the bus angle. The bus angle is your rotor angle, right? And the bus voltage magnitude, it is associated with voltage instability. So they are more or less related. Yeah. But there is, when we have these two stability analysis, when we talk about the rotor angle stability, we will say about one generator, right? We will say about one generator with respect to a large network here. So remember one thing, rotor angle stability, we said that relative motion between one generator with respect to a large network or with respect to another generator. So it will be, we are saying it for one generator. But when we say it for voltage stability, here it could be you have some large network and then to a small section of a load consumer end actually. So there is some reason here. All right, there is some small reason or a local reason here where you have high concentration of consumers or the load here, right? And this large network feeds power through this line to this section of the load consumers here. So that is referred to voltage stability. So here we talk about a one local area, but for angle stability, we talk about a one generator here. That is somewhat difference between the two. But again, remember these two forms, they are dependent on each other. And let me tell you, uh, if there is a cascade outage or if there is a blackout occurrence, then one form of instability will translate into another form of instability. So if I say, for example, the uh, following the disturbance, rotor angle deviates out. Okay, so that means the initiation of instability, it is because of rotor angle. Okay, but when you have the initiation of the rotor angle instability, then let's say one of the generator fails, it is outage, then your load remains connected still. Then it is possible that the voltage at the load center end, right, the voltage at the bus load end, it drops actually, progressively it drops. Okay, there is a cascade drop here, progressively drop, and that may result to voltage instability. So that is example saying that if the rotor angle between the groups of the generator reaches about 180 degree, it will result to the loss of synchronism, and as a result, the voltage at the bus will also drop in the network. So the initiation of instability, it is because of angle, and later on it translates into voltage instability here. So that means that the blackout occurrence, initiation because of angle instability, and later on converting into voltage instability here. This is one example. Then again, the loss of synchronism for some sets of the generator, right? Uh, that means here you have initiation of voltage instability. That's, let's say that you have sudden a large amount of load connected, and you are not able to maintain or restore the voltage at that bus, and as a result, the generator which is connected to the bus will lose the synchronism with respect to the other. So the initiation of instability, it is voltage, yeah, and as a result, uh, in fact it will violate the field circuit field current limits, and thereby it is also possible to translate into frequency instability. That is also possible, right? So this is, so you can't say that instability in the system, it is just because of one form of instability. It could be, in most of the cases we observe that there are two forms of instability occurrence leading to blackout occurrence. Yeah. Okay. In most of the cases, most of the examples. Yeah. Right. Because if I take this example, which I had it, I mean this one, what I know, this one, yeah, this one. Because in this event, there was some stress in the transmission lines, which we had it in the southern of Sweden, and because some of the generators were forced outage because there was some maintenance being carried out on nuclear power plants here, and the transmission lines were stressed, and then there was some maloperation in the relay, and as a result, voltage collapse took place here in southern of the lines here, southern located lines. And so thus the initiation of the instability, it was voltage, and later on it translated into the loss of synchronism between the generators here. So that is the example here actually, where we have two different forms of instability associated with the blackout here.
So the reason for this incident was the malfunction of one of the relays. It didn't trip the line, or
Yeah. Remember one thing. In most of the cases, because when we refer to the report of the blackout occurrence, we observe that uh, before the blackout occurrence, before the blackout occurrence, the frequency in the system, it is very much stable. The voltage in the system, it is very much stable, all right, within the nominal value. But the system is stress. The system is stressed. So that means very highly, because let's say you don't have much generation and you have high demand, though you are able to control your system, you are able to regulate your generator to meet the demand, all that. uh, in that it is possible that some of the lines, right, because let's say if you have several generators in a network, and you have the load, right, so all the generators, they are feeding power to the load, no problem, this is okay condition. But let's say that during some period of time, some of the generators, they are forced outage. Let's say that you want to carry out on certain generators in one power plant, right, you have some maintenance being planned today, right, this is today. So you have some maintenance being carried out on the generators for 1 day, 2 day. Then again, let's say another section of the network, let's say after 2 days, still the generator outage is there. And let's say you have some other section where there is a transfer, there is some maintenance being carried out on the line. So what happens, the line is cut, all right, that means the load which is connected to that line, it will be fed power to through some other line, right. Then again, this generator, it is force outage. So that means there will be some other generators which will be overloaded to feed power, because the load is still intact, load is not set, load remains connected, but the line is cut because of the maintenance, generator is cut because of the maintenance. So the system is stressed now. Now, with this stress condition operation of your network, if there is some mal-operation or some disturbance, there it becomes very difficult to control, right? And that is more important for us. If you are able to control, if you are able to regulate your generator, your system operation for those contingency level, for those events, disturbance, right, then if we can
because there is no margin, because it's already stressed.
yeah, that is that you can say there is no margin. Yeah, you're right actually, because it is very difficult in those situations, because mainly for the such events, it is very difficult to regulate our network, regulate our generators, and that results into tripping of the generators or the lines, and then cascading outage. Because just you can see the instability takes place in just few seconds. It's just 3 seconds, 4 seconds, or 7 or 10 seconds only, right? And if your system operators, they are able to act upon, if they are able to regulate your network in 7 or 10 seconds, then they can restore back, they can restore back to the equilibrium state, and thereby get the system stable. And if they are not able to, within that time frame, if they are not able to restore it back to the new state of equilibrium, then it will be unstable. That happens actually.
So in case of maintenance, wouldn't it be better to do some load shedding beforehand, so to avoid this problem?
But again,
Because
if you do the, let's say you are doing some maintenance on the line, and then, or even on the generator, and let's say that there is a load shedding, but is it allowable? Is it allowable? Because even the customer, they will complain why we have the load shedding.
Yeah, but it's not under your control. You must do some maintenance from time to time, right?
Yes, but
So,
again, let me tell you, in in most of the planning of your network, we always say that okay, this city, if it is fed power from this power plant, and let's say that this power plant has some maintenance or outage, then the same city has to be fed power from another section of the line. Do we plan or no? We always plan that.
yeah, you have to
Yes, we
plan
always
this,
plan.
of course.
So because that we cannot in fact tolerate actually, because the power cut we cannot tolerate actually, because everything is dependent on your power. So even if it is a plan, even if it is a plan, it is very much important that the power supply has to be restored. It has to be restored even in the planning. That is important actually, and that's why actually nowadays, remember, we talk about resiliency, because let's say because now we have the microgrids in the system, and then let's say there is some earthquake, or let's say there is some thunderstorm, and there is some breakage of the lines and so on, right? Then nowadays we talk about resiliency. That means even under those situations of natural disasters, we should be able to restore our power supply to the consumers. So we talk about resiliency now. So that means we can't afford the disruption of the power supply to our consumers. We can't afford that, right? But it's because the power network is wide actually, because it is not just one generator or just one power plant, right? It's a widespread, geographically widespread network, and thus it is very important. In fact, it is sometimes very difficult to maintain it in a controllable way unless we have some way of monitoring the entire network, and then having some information exchange between the system operators and the power plant operators, and thereby regulate it accordingly. So in fact, I think yesterday I said that you can have some YouTube lectures on the YouTube available, and you can refer that about the background on the stability. Then I just move on to the next slide. Here we have it for small signal stability, and this we call it as a small disturbance stability or steady state stability. And this small signal stability we talk about, it is the ability to maintain synchronism against small disturbances. So we talk about the synchronism in the system uh, only for against small disturbances here. So in this case, the disturbance is small to an extent that the differential equations that describe the dynamic response of the power system, they are linearized here for analysis purpose. So that means the disturbance is small to an extent for which the nonlinear equations that describe the system can be linearized for our analysis here. That is what we say about the small signal stability analysis. And we say that the disturbance, if it occurs, it will result into some changes and it will disappear. So that means disturbance will not exist for a longer duration. It just occurs at time is equal to t is equal to 0 plus, and then thereafter it disappears. That is. Under this small signal disturbance, uh, in fact, the power system can remain stable. It can remain stable if it returns to the original state or a stable or a state of equilibrium point. So if this happens, that means if system regains back the equilibrium state of condition, following this small disturbance, then the system will be stable here. And for all those kinds of small signal stability analysis, we have a linear model of the power system. We have the linearization of the model. So here I have one slide to tell you about how we perform small signal stability analysis. Normally we have, let's say, the power system model. Now, your generator, right? It is a synchronous generator mainly, right? And synchronous generator model equation, the differential equations that describes the dynamics of the synchronous generator. It could be of as high as something seventh order model, or it could be sixth order model. So that means the generator state equations could be sixth order. And again, a non-linear model. You have some not only the first order equations but also the second order equations here describing the system behavior. Then you have the generator, and then the generator will have excitation system, and then you have automatic voltage regulator, and then you have the governor. So a single generator will have some auxiliary equipments also, the excitation systems, the governor, and again the turbine as well. A single generator. The single generator, it is you will have excitation system, governor, turbine, right? And thus then the complete generator, it is connected through transformer, through the line, and then load and so on, right? Now, what you say about the transformer and the line? There, if you have to model it, what do they represent? Do they represent some dynamics? Yeah. Do the transformer represent any dynamic behavior?
What do you mean?
By the word dynamic means if there is some disturbance, the system parameter will change. So if I say there is some behavior, some disturbance, do you think that the behavior of the transformer will change?
It might change if you have saturation, for example.
Okay, okay.
Yeah, it will definitely
If you,
change in that case.
okay, that I agree with you, because if you want to model your transformer for short circuit, for fault analysis, then you have to take into account the saturation effect, and then you have to decide the relay setting, relay operation, and the circuit breaker. That at that point I agree. There you have to take this saturation effect also. That will be a non-linear model of a transformer. I agree. But if you talk about in terms of rotor angle or the frequency stability or the generator, with respect to the generator, because transformer is a stationary device, stationary equipment. Am I right?
Yes.
So that means the uh, you will observe some deviation in the voltage magnitude and so on, right? But the reactance of the generator will change or no? System parameter.
No.
It will be
No.
constant. It will be constant. That means the transformer being a static device, it is a static device, and thus it will be not very much dynamic in nature for a load disturbance or a line trip. Actually, I'm not talking about the fault, right? I'm talking about the line
Yeah.
trip.
So
Or
assuming
the,
it does not,
yeah,
saturation does not occur.
yeah, that's fine. And another, let's say the line is represented by a impedance. It will the series combination of resistance and inductance, and even if you can consider the capacitance and shunt. So, but the resistance of the line, inductance of the line, or the capacitance of the line, those are static. The parameters will not change, and thus it is static. So, thus the line is also a linear model, right? Transformer can be a linear model. What about the load?
The load is not linear at all.
Which type of load?
I mean, if you have a motor, for example, or if you have some kind of load that is unknown.
Yeah, motor is a non-linear because motor involves the dynamic, because because if you consider the motor operation and you have the change, dynamic involved in the rotor. In fact, the speed, basically the speed here, the speed of the motor here, right? It will change.
Yeah.
And then
If you have a rectifier also.
yeah, rectifier types, all electronic loads. Then
Yeah.
if you talk about the electric arc furnace, those are actually all as a non-linear load. But if you consider lighting load, those are static load actually.
Yeah, yeah.
But again, loads can be as a composite load modeling. So sometimes we say static load or sometimes we say dynamic load. But overall, the power network, it is actually a dynamic. And this dynamic behavior, it is actually because of your generator and including the turbine here. So the your power system, it is dynamic in nature. But for small signal stability analysis, we can always linearize them. That is possible. And for a linear representation of the dynamic model, we use a differential equation. We use a differential equation. So what is this actually? This is actually delta. Delta change in the state variable, right? Remember, if your last semester, we have derived the state space equations. Do you remember?
Yeah.
Yeah. So the state space. So this is actually a form of the state space equation here. So we have x1 dot, x2 dot, x3 dot. So these are the state equations. And these state equations, we derive it from differential equations here, dx by dt basically. So here this term delta refers to the small change in the state variable. And it is actually rate of change of small change in the state variable. And this is equal to A times delta x. So A is actually the state space matrix here. That is the matrix A here. So if you are able to obtain a linear equation for the dynamic power system model, then with the given matrix A, you can always obtain the eigenvalues here. All right. And using the MATLAB function EIG, you can always obtain the eigenvalues from the matrix. And with this, we have obtained the eigenvalue. And from this eigenvalue representation, because you may have a conjugate eigenvalue, so it will have some real part and it will have imaginary part here. So it is a conjugate eigenvalue here. So it is the real part and imaginary part. And with these conjugate eigenvalues, you can plot them on S-plane. That is Laplace S transform plane. So here what you have it here, the real part and the imaginary part on the y-axis. So this is your S-plane. And for the S-plane, this side of the region, we call it as right-hand side, and this side, we call it as left-hand side. And depending upon if the eigenvalues on the S-plane, they are located on the left-hand side, then let's say these are the conjugate eigenvalues here, right? So if the eigenvalues are located on the left-hand side, it is very much obvious that following the disturbance, a small disturbance, let's say the system behavior associated to this eigenvalue, it is power, electrical power flow. So with the location of the eigenvalues on the left-hand side, the dynamic of the state variable, electric power, following the disturbance will have few oscillation. All right, it will have few oscillation, and then it will settle down to the steady state point here, and it is in few seconds. So that means if you have the location of eigenvalues, it is very much obvious that the state variable will be a stable, and thus the response will be a stable here. There will be some perturbation, some deviation observed following the disturbance, but it will settle down either on the either at original point, original equilibrium, or it can even settle down to the new steady state point. That is also possible. So but the system response will be stable here. But if in case these eigenvalues which you obtain, they are on the right hand side, then it is very much obvious that the active power, the electrical power following the disturbance will have a oscillation. All right, there will be an oscillated response. And what we observe that since the eigenvalues are located on the right hand side, there will be a increased amplitude of oscillation here. If you find it, there is an exponential increase. There is an exponential increase in the magnitude of oscillation here. Okay, if you have it on right hand side, and thus the system response is unstable, right? Then what about if you have the eigenvalues on the imaginary axis? Yeah,
It will be oscillating, but at a constant rate. It will
yeah,
not
yeah.
damp.
It will not damp. So because here you find the system response is damped out. And this case, it is undamped basically, right? But if you have the location on the imaginary axis, the system response, it is actually, it just oscillates at a certain magnitude here. Or it is an oscillated response here. It is not damped out. So this oscillation does not damp out here, right? You can have more details about this analysis on the in the Kundur book, yeah? Or maybe we will also discuss more in detail later on. So, is it possible that we can stabilize these situations here?
If you add a controller to change the
It is
eigenvalues,
possible.
then
It is
yes.
possible, yeah. So
Yeah.
now it is very important that how we are able to stabilize the system response for these situations, either either a oscillated response or a undamped response here. Yeah. We can refer some more study about the small signal stability analysis on the YouTube. Uh, it is available how to perform the small signal stability analysis. So next, you will like to have a break here for 5 minutes.
Yeah, that
Okay,
would be
fine.
nice.
Okay, good. Maybe I. All right. So now I just want to have a little bit brief about what is power oscillations. Normally, you should be aware that in a power network, the generators and the loads there are interconnected to the line. There will be several lines, and thus the complete network. And we intend to operate the generators in synchronism at a constant system frequency. And if in case speed of one generator uh, deviates from the synchronous speed value, then this will result into the power flow in the network. And if this takes place, if that means speed of one generator being deviating out, then in that situation, it is important that we maintain the synchronous speed uh, of the generator, of that particular generator, by applying some regulation, by applying some control action. That means you change the control parameters. All right, and it could be either on the exciter side or it could be on the governor side, that is on the turbine side. So that means whenever there is some deviation, in the system variables, right, then the control action has to take place. There should be a appropriate level. It is said appropriate level because some control actions may not be appropriate to maintain, to achieve the synchronism. All right. So it is very important that the gains of the controller, they are set in such a way that the system is restored back to a stable state, or thus the deviation in the state variable is minimized or eliminated to zero. There's because if I say deviation in the frequency is zero, it means that the system frequency is exactly 50 hertz, right? So, but if there is some deviation in the 50 hertz in the system frequency, if there is either plus side or the minus side, it is obvious that there is some mismatch, and you don't have I will not say you don't have a good level of control action being achieved here, I will say. Normally, in related to the low frequency power oscillations, this can take place because of the setting of the gains of the controller, or in some case the network state of the network it is inadequate. By the word inadequate, it means because normally we don't have any uh, concrete reason to say why low frequency oscillation takes place actually. Uh, Although it is related to the gain setting of the exciters, but even if the gain settings of the exciters they are good enough, but in some situations maybe either because of the property of the system, network property, impedance property, or even the load and so on, uh, in some cases we observe low frequency oscillation. Yeah. Particularly we say that the high speed excitation systems here. High speed excitation systems are those which are static excitation system, and which we normally use to uh, prevent the synchronizing torque, prevent the loss of synchronizing torque, and thereby improve the stability, transient stability. But use of high speed excitation systems, it weakens the damping torque, yeah, and thereby resulting into low frequency oscillations. I will discuss more in detail later on. uh, with the electromagnetic torque, it is actually the phasor sum of synchronizing torque and the damping torque. And if because of high speed excitation systems, the damping torque becomes poorer, and this results into low frequency oscillations. And this damping torque, it is because of you can say even because of inertia of the system. uh, do you understand by the inertia?
Yes, I think you explained that last semester about
Yeah,
the generator inertia, like
generator
how
inertia.
much, yeah, how much the frequency change will affect the speed or something,
Indeed,
how
and also, yeah.
power change will
Yeah,
affect it.
yeah, yeah, you're right. Because if you have synchronous generators, they have the inertia introduced in the system. But if you installed PV system, the inverter-based renewable resources, I mean, so they don't have any inertia. But you add power from them, from the renewable resources PV systems, but you don't add inertia, and thus you don't introduce sufficient damping torque here, damping characteristic, and that could also be another reason for the existence of low frequency power oscillation. So then going further, there could be periodic variations in the generator angle, or you can say the bus angle in the network, uh, and this can occur because of changes in the load, step changes in the load, or maybe some sudden change in the generator output, or maybe the line switching, or even short circuit fault here. Now, what is shown here, you have these oscillations, and this is with respect to time. You find that you have some oscillation. This is something, but again, you observe that following the disturbance, there is some oscillation, but the oscillation is damped out. Here, the oscillation is damped out. And what you observe that it is the oscillation is at 0.8 hertz, and but the damping factor, the damping ratio, it is poorer. It is plus 2% only because it is damped out. So the damping ratio, the damping factor is positive, right? But if there is no damping ratio or the damping factor, if I say 0%, for the same oscillation, for the same frequency of oscillation, the oscillation will persist, it will adjust, it will be a constant amplitude oscillation, and this is for 0%, right? And if there is a poor or negative damping, if there is a negative damping, then for the same mode of oscillation, same frequency of oscillation, what we observe that the oscillation amplitude keeps on increasing here. So thus the damping, either negative value or the zero value or even the plus value, positive value, they are important. They are important for the power oscillations here. If it is a positive, the oscillation will damp out. If it is zero, then it will persist, it will remain. And if it is negative, the damping ratio is negative, so it will be always increasing. So you can refer here, I think this one. Sorry, I think it was somewhere here. Yeah, if I just call back here, because if you have the location of the eigenvalues on the right hand side, the damping ratio will be negative. If you have the location of the eigenvalues on the imaginary axis, the damping ratio will be 0%. But if you have the location of the eigenvalues on the left hand side, it will be always positive. So that means it is this quantity, it is this real value, and then the sign associated with the real value that influence the damping ratio. If it is positive, you have the location here, and if it is absent, then you have the location here, and if it is negative, you have the location here, right? Yeah. So next one, I think earlier also somebody has asked that what about the oscillations? It is possible that some generator, as you can see here, they have this oscillation, and another sets of the generator they have this oscillation. So it is possible that some sets of the generator they have phase opposition oscillation. So that means the deviation in the speed here, if you draw the phasor here, if you draw the phasor for the two generators, the deviation in the speed signal, they are anti-phase here, and this is actually the phase opposition oscillation. Now it is also possible that some generators they will oscillate at a higher amplitude, and while other generators they will oscillate at much lower amplitude, but altogether all those generators will oscillate in the same phase of oscillation. They will be oscillating in the same phase, and thus they can be in phase oscillation. So thus the phasor for the speed deviation, depending upon the length of the, that is the magnitude, because this black one dash line, it is much higher amplitude. So but all the phasors will be in the same line, but they will be in the same phase actually here, right? Next one, in fact, these power oscillations, we have different forms of the power oscillation being observed. Earlier, in fact, decades back, around 2 decades back or 3 decades back, we only talked about a few forms of oscillations. But over the years, what we have done, we have more interconnected network, right? We have several grids formation, right? We have national grid formation and we have the continental grid formation as well, right? And as such, the system has become more complex because now if I take the example of not a grid, because in Norway, all the generators, they are hydro generators actually, right? Because most of the power source, it is from hydropower. Now, if you look into the Sweden region, there you have a little bit mix of it. So because there you have some nuclear power plants as well, and even some wind farm as well. Now, if you look into the Denmark side, mostly it is dominated by wind turbines, wind farms, at least 50 to 60%. And then again, you also have coal-based power plants. Then again, same way, if you look into Finland, there you mainly you have nuclear power plants and thermal power plants. So now you have the complete network where the dynamics of these generators, they are different. Hydro generators, steam turbine basically, or the steam generators, thermal generators, or the wind turbines through the wind farms, they are different actually. So as a result, we have different forms of oscillation being observed in our existing network, and thus there had been some more classification over the years actually. So these power oscillations, we have classified them into as natural and unnatural. In the natural one, we say it as inter-area mode and the local mode of oscillation. Then again, in the inter-area mode, it could be a damped oscillation or a weakly damped, that means slightly less damped. Then local mode of oscillations, again, well damped or the weakly damped. Unknown natural oscillations, in this case, they are actually basically as limits. That means you find some oscillations of few cycles, but that is for a limited duration, that's all. And then because of some what to say it as because of periodic action of load, uh, you have some type of forced oscillations, and these oscillations, they are basically as a sustained oscillations. And again, that's why this classification of oscillations which we have referred, they are unnatural, because for these oscillations the actual reason, it is still not very much known to us. We are still working on what is the exact reason and how we can minimize the occurrence of such oscillations which exist now in our power system, right? So this is actually the general classification of power oscillations in the system. Anything on this? Okay, right. Move to the next one. So as a whole, I hope you can hear me, right?
Yeah, we can hear you just
Okay,
fine.
fine. So just because sometimes, although I could see the I could see this red color dot. So it means I'm connected. So, but in general, if we look into in a broad sense, we have two forms of oscillations. One is the inter-area oscillations. Another one is the local mode of oscillations. Now, what is inter-area oscillations? In this case, we have two groups of the generators which will swing against each other. So that means you have two groups of the generators. They are connected by a long line and they are swinging against each other. So when we say swinging against each other, it means that the phase of oscillation associated with inter-area oscillation will be either there is a phase shift or it will be a phase opposition, more or less. So thus these groups of the generators will be in most of the cases they will be oscillating at a anti-phase, or is there is a phase shift, that means this one. So inter-area oscillations, in this case, mainly we observe either a phase shift or the phase opposition. But Local mode of oscillations, here we have the oscillations in few sets of the generators. It will be, let's say you have 4 or 5 generators in one power plant, and we observe the oscillations in these sets of the generators in the power plant, and they will be oscillating against the rest of the network. So that means few sets of the generator in the power plant, they will oscillate against the network, against the rest of the system. And in these cases, normally we observe that uh, when we have all these generators in one power plant, we observe that their oscillation in more or less they are in the same phase of oscillation. So that is the peculiar property we observe here between the two mode, either local mode and inter area. Then another one, we say that inter area oscillations, they are comparatively lower, much 0.1 hertz to zero point 0.7 or zero point 0.8 hertz even. But local mode of oscillation, they are somewhat higher. 1 point, but again, this is a very much general, but because it will again vary with the power system, vary with the power network. It is in the range, but it comparatively it is higher comparatively. Here, several generators and the areas. That means you have several generators and there is an involvement of area as well. They will oscillate. They will involve the oscillation. But here you have some or all generators in the same network, in the same power plant or in the same area. They will be oscillating against the rest of the system. Right? That is the difference between the two mode of oscillations. Yeah. So for the analysis purpose, uh, we have the eigenvalue or the eigenvectors analysis, that we call it as model analysis. We call it as model analysis to determine the stability of the network. So as I said earlier, we have the dynamic system, we linearize the model, we obtain the state space equations, state equations. Then from the eigenvalue, this is how we have the eigenvalue defined. Yeah, this should be minus here, sign. Then this is how we define the frequency of oscillation. And this is in hertz. This
I have
omega,
a question.
yeah.
In the previous slide about inter area oscillations and then the local mode oscillation, it says there that a small number of generators um, oscillate against the rest of the system, but they still maintain phase. Is that correct?
You mean say inter area?
No, 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 local mode oscillation.
Yeah, yeah.
When
It
you
is
went
either
to the next slide, you said that they maintain the phase.
this one.
No, no, no. There's a slide that you said that there's a next slide. I actually don't see
This
it
one.
in the, yeah,
Yeah,
that one.
yeah, this one. Okay.
So how does that happen? How do they maintain the phase, and yet for the section where only two groups of generators swing against each other, they're not able to maintain the phase?
Okay. So I think you want to know that because mainly when we have local mode of oscillations, these oscillations we observe in some generators located in the power plant, right? Let's say because you have 7 generators in the power plant, right? 7 generators in one power plant, and you normally when you have these generators, they are all of the same rating normally. If it is 100 MVA for each set, so that means you have 7 generators into 100 MVA, that means 700 MVA. So all these generators, they are of the same rating. Am I right? And then the controllers or the turbine, the governors, exciters, when you have them for these sets of the generators, which are of same rating, they will be the similar, right? Now, but the governor settings and the exciter settings, they are almost same actually, right? But for some situation, we observe that these generators, these some of the generators in the power plant, they will be oscillating in among themselves, All right, so that means they will be oscillating. The oscillation will be observed only on these generators. These oscillations will not be observed in other generators in the other power plant. You will observe these oscillations in the generators which is located in one power plant or in one area only. Okay, you don't observe the same mode of oscillation, either zero point 0.7 hertz or the zero point 0.8 hertz between the generators, or the in the generators which are located somewhere else. We don't observe that actually. So the local mode, that's why it is a local. So that means the mode of oscillations will be among the certain sets of the generators which are located locally. That means which are in the same power plant or in the same area basically, right? So that's, and these generators either in the same power plant or in the same area, they will be oscillating against the rest of the system. So it means that these oscillations will be only in these sets of the generator. You don't observe the oscillations in another sets of the generator. It will be only in these sets of the generator. Okay.
Does it mean that if there's any change in phase, it will be limited to only
Only
the
one, only, oh yeah, it will be limited to only certain group of the generators, and those group of generators in the same power plant or in the same area. Why I say area? Let's say that you have one 500 MVA power plant, right? And then and this power plant is connected to another 500 or 600 MVA by a distance of something 50 kilometer. So thus you have two power plants which are just at a short distance, 50 kilometer. So we normally, and now these two power plants, they are connected to a large network, to the same transmission line, a large network. Okay. So we observe that the dynamics of the generators which are so nearby, okay, they are almost the same. They are almost the same. And that's why it is said that the dynamics of the generator, that means the oscillation of the generators, either in the same power plant or in the same area, nearby area, they will be uh, in the local mode and they will be oscillating against the rest of the system. Yeah. Right. Okay. Okay. Is it okay? Fine. So that's here we have the eigenvalue defined by these two terms, and then this is the frequency of oscillation. This is how we obtain in hertz. This is how we define the damping ratio, right? The damping ratio, that is actually the ratio of the real part, and the it is actually the, you can say, the square root of square of the real and the imaginary part here. Then I will discuss more in detail later on. From the model analysis, we can know the mode shape. By the word modes, because here I said that what is the phase of oscillation? Either they are in the opposite phase of oscillation or they are in the same phase of oscillation. So it is actually the mode shape. It is the mode shape that tells you how does the two generators are oscillating with respect to each other. And for that, we have to actually compute eigenvector. I will discuss more in detail later on in the exercise when we do how to calculate the eigenvector. So from the eigenvector, we calculate from here, we calculate the left eigenvector and the right eigenvector. And from there, we define the mode shape here. And in general, what we find here that the modes and the eigenvalues, how they are located on the S-plane, right? Now, in fact, we say the system mode actually, but those modes which are associated with rotor angle, because you remember one thing, when we say the rotor angle, it is actually a physical variable because it is space angle, it is in space actually, because when you say the angle between the mmf vector, it is in space, and when the same MMF factor, it translates into electrical quantity, let's say in terms of voltage, then it will be as a electrical quantity. We say it as a voltage angle. So, but in both the cases, we say the angle as of electromechanical nature, because it is related to the electrical quantity and as well as mechanical quantity space, mechanical variable. And thus uh, the quantity associated with the angle, the mode of oscillation, it is inter-area oscillations or the local modes, they are actually as electromechanical. Sometimes we also say electromechanical oscillations or the rotor angle oscillations or the power oscillations. Yeah. So this is electromechanical oscillation. It is the same. When we say electromechanical, it refers to the rotor angle oscillations or the power angle oscillations. Yeah. Now, on the S plane, we find that the inter-area modes, yeah, the location of the eigenvalues which corresponds to the inter-area mode, they are here. The local modes, they are somewhere here. And those modes which are associated with a control variable, let's say the exciter control is state variable or the turbine state variable, they are somewhat located here. Now this we can refer, because if you look back here, because it is this mode omega value, okay. And if you go back, just see the local mode of oscillations, they had much higher frequency. The omega radian per second, it will be much more as comparable to inter-area. Inter-area mode of oscillation in hertz or the radian per second, it is less. And thus the omega quantity, omega value for the inter-area mode, because on this axis you have omega. So they are somewhat here. But the local mode, they will be located somewhere here. And the control mode, they are located somewhere here. Right. So maybe I will stop here. Okay. Anything
Okay.
on this? Yeah. I would request that you all should go through this lecture. I mean, which is on the YouTube. I will try to upload, because I will try to upload on the Canvas. But request you to go through the lectures which I have on the YouTube. All right, so that you get sufficient background on the system stability here. So you go through these lectures, and in fact, it is for several days, or it is, but try to get, because now we have this course next week. So you have 1 week of time. So try to get some of these videos attended actually. Okay. I will try to upload it on the Canvas also. I will do that by this week. Okay. So I stop here now.